Up until this point, we've been looking at single weak acids in solution. If we do have a mixture of acids and we want to find the pH of it, typically we only have to look at the strongest of those acids. So if we have a strong acid mixed with a weak acid, we look just at the contribution of the H3O plus from that strong acid. Because I'll show you this on the next slide when we have equations, but if we think about Le Chatelier's principle, when that strong acid dissociates, produces H3O plus, that H3O plus is going to shift our equilibrium of the weak acid towards the reactants, or towards the undissociated, unbroken up acid, molecular acid. And so that becomes negligible. The amount of H3O plus that is contributed by the weak acid is negligible. Now if we have a mixture of weak acids, same idea applies. So we look at the strongest of the weak acids to figure out the concentration and therefore the pH. So if we look at the pH of, or if we're trying to find the pH of a mixture of acids, here we have HF and we have HClO2, and we look and we see the Kas for each of these acids. So we look at HF and its reaction, we look at HClO2, and I'm missing a 2 in my subscripts. Okay, we look at its Ka, and we also have to remember we have the contribution of water. So if we look at these 3 Kas, or Kw for water, which one is going to be the strongest? The HF is going to be the strongest because it has the largest Ka value. So this is going to be the greatest contribution to our H3O plus. Once we form the H3O plus, that's essentially like adding product into our HClO2 reaction here, which shifts it towards the reactants. And so most of it is going to stay in the molecular form. And Kw is even more so. Okay, so to find our pH, we are going to again do our ice table. So we're looking at HF, its conjugate base, and the H3O plus. So we write our ice table. We know our initial concentration of HF. And for our products, it's going to be 0. Our change for the reactants is going to decrease, and our products are going to increase. So if we add these together to figure out at equilibrium, we have the amounts at equilibrium. Because we're only considering the strongest acid, we're going to write the Ka formula for that. Products over reactants. And we can substitute in the values here. So X for our fluoride, X for the H3O plus, and again, we're going to assume that the X is small, so this is just going to be the contribution or our initial concentration of HF. Right? If we rearrange this, our X is going to be the square root of our Ka times the initial concentration. So X equals 7.2 times 10 to the negative third. So if we want to find our pH, it's a negative log of that value. So even when we have a mixture, we still are just looking at the strongest of the acids in the mixture. Okay, so here is a practice for you to determine. So I'm going to ask you to pause the video, see if you can figure out what the pH is of a mixture of HCl and HF. All right, so in order to determine this pH, we need to recognize that HCl is a strong acid, which means we don't have a Ka. HF is a weak acid, so some of it's going to stay in the molecular form. And so to find our H3O plus concentration, we don't even need an ice table. All we need to do is use the concentration of our strong acid, because it's going to nearly 100% dissociate into the ions. And so we can just take the pH of, or the negative log of this concentration to find the pH. So it does differ if we have a strong acid or a weak acid. So our HCl is going to be our main component that is contributing to the pH of this particular mixture. Thank you.